So in the last section, we talked about a sequence, which is an infinite ordered list of numbers, A0, A1, A2, A3. And we talked about ways to find patterns in this list of numbers and to find out what they converge to. Now for every sequence, there's a corresponding idea, what's called its series. That's what we get when we take the numbers of a sequence and we add them up. The symbol that we use for this generically is summation, AN. And so, once again, we have a sequence, which is a list, and we have a series, which is a sum. Now, I should be a little bit more precise about this, because how do you really add an infinite number of things? This is just like a Taylor series, a formal infinite sum. We can't actually add up an infinite number of things. How we think of it, though, is we sort of think of this as describing a fixed number, whereas a sequence is a list of numbers. A series is describing a single particular number. It's describing the number who could be approximated by A, but a better approximation would be A0 plus A1. A better approximation would be A0 plus A1 plus A2. A better approximation would be A0 plus A1 plus A2 plus A3, and on down the line. So in the back of our minds, a series is a formal sum that represents a single number formed by the successive addition of the terms of a sequence. So how would you figure out what this number is? We could make a list of what these approximations are. So our first approximation, S0, would be A0. An even better approximation would be A0 plus A1. An even better approximation would be A0 plus A1 plus A2. An even better approximation would be A0 plus A1 plus A2 plus A3. Oops, somehow I lost that 2. And in general, we could get better and better approximations. This right here is another ordered list. It's another sequence. It's sometimes called the sequence of partial sums, because what we're doing is we're adding up a part of the sequence each time. We're not ever getting to all infinitely many of them, but we get more and more terms, which is hopefully a better and better approximation. Then when we have this list, then we can talk about the series AN as being nothing more than the limit of this sequence of partial sums. Because limits measure, whether or not the terms are approximating something, and each one of these terms is supposed to be approximating what the sum is. So, the series is equal to the limit of partial sums, provided this sum exists. The best way to try doing this is through some examples first. So let's take a look at several examples, and then we'll put some theory behind it. Let's evaluate the sum, n going from 0 to infinity, of 1 over 2n. So, what does that mean? It means we're taking the sequence 1 over 2n. So if we start that sequence out, that would be 1, 1/2, 1/4, 1/8, 1/16, 1/32, ... But instead of listing them, we are adding them successively. So we want to figure out whether or not this infinite list of numbers is honing in on something specific. So let's see what we get by adding up successive terms. If we add up only the first term, we get 1. If we add up the first two terms, that's 1 plus 1/2. That would be 3/2. If we add up the first 3 terms, we're going to have 1 plus 1/2, which is 3/2, and then we're going to add a 4th to that. So putting these things on a common denominator of 4, we're going to have 6 plus 1, or 7/4. If we add up the first 4 terms, we're going to have the first 3 terms added up, which we've already worked out as being 7/4, and then we'll add an 1/8 to it. So putting that on a common denominator of 8, we're going to have 14 plus 1, 15/8. And if we add up to the 16th term, it's going to be the sum of the first 4 terms, which we've worked out to be 15/8 plus 1/16. Adding those things together, putting them on a common denominator, we'll have 30 plus 1, or 31/16. And so by adding up the terms of this series, we've built a new sequence of numbers. The sequence 1, 3 halves, 7 fourths, 15 eighths, 31 sixteenths, which is called the sequence of partial sums. So remember that the series of 1 over 2n is equal to whatever this limit, or whatever the sequence of partial sums converges to. So we talked about how to do sequences in the previous one. What we need to be able to do is we need to come up with a formula for these guys. Once we have the formula, we can figure out whether we could use, say, the underlying function principle, or even an odd analysis, or something else. So, well, let's see if we can do that. To come up with a a formula for this sequence, our SNs, well, let's take a look first. We have fractions, and in our fractions, the denominators go 1 to 2 to 4 to 8 to 16. The denominators are increasing by 2's, which makes them a geometric sequence, starting at 1, and going up by 2's each time. The numerator, well, let's see, 1 to 3, 3 to 4, 4 to 15, 15 to 31. It might take a little bit of finagling to figure out what's happening on the top. But if you were to add 1 to the top each time, the list of numerators, if we added 1 to the top, would be 2, 4, 8, 16, 32. The top, if we added 1 to each term, would be another geometric sequence. It'd be the sequence 2 times 2 to the n. But it's always 1 less than that. And so we've come up with a formula for the sequence. 2 to the n plus 1 minus 1 over 2 to the n. And so now we can take a limit of the sequence because we've got a formula for it. It's going to be the limit of 2 to the n plus 1 minus 1 over 2 to the n. First thing I'm going to do is switch all of those x's, or n's for x's, so I can talk about underlying functions and use the full power of our calc techniques. So this function right here, is it an underlying function? Remember, that's a check really about the number of critical points it has. So we can look for discontinuities, not a single one of them. We can also look for trig, not a single one of them. So no discontinuities, no trig, this is an underlying function. So now I can take the limit using any of the tools we've got. This is not a bad example to do L'Hopital's rule on, but I'm actually going to use a little bit of algebra instead. Let me just split the denominator. Split the numerator over the two denominators to make life a little bit easier. When I do this split, the first term, 2 to the x plus 1 over 2 to the x, just simplifies to 2. And the second term simplifies, well, just to 1 over 2 to the x. Now if I let x tend off to infinity, the 2 doesn't change. 2 to the infinity is an infinite power, and as a limit, we know that that's 0. And so it turns out that this sequence of partial sums, this infinite series, is equal to 2. Let's evaluate the series, the summation from 1 to infinity of 1 over n times n plus 1. So remember, a series is a sequence whose terms have been added up. The sequence is this expression right in here. So let's work out the first several terms of the sequence. So when n is equal to 1, I get 1 over 1 times 2. When n is equal to 2, I get 1 over 2 times 3. When n is equal to 3, I get 1 over 3 times 4. When n is equal to 4, I get 1 over 4 times 5. Right, that's the list, the sequence. The series is what I get by adding up the terms of this sequence. Now, I'm thinking that this series is supposed to be an approximation of some fixed number, some specific number, and I'm giving you successive approximations of it. But what number? Well, let's look at the partial sums again. The first partial sum would be 1/2. The second partial sum would be 1/2 plus 1/6. Put that on a common denominator, that would be 4/6 or 2/3. The third partial sum was going to be, well, the sum of the first two, which we've worked out to be 2/3, plus 1/12. Putting those on a common denominator of 12, we're going to have 9/12, which simplifies to 3/4. if I add up the first four numbers, we have the sum of the first three, which we've worked out to be 3/4, and then we're going to add 1/20. Put them on a common denominator of 20, we'll have 15 plus 1, 16/20, and 16/20 is 4/5. And we can keep this on. So from the series of numbers, we've built a sequence of partial terms. The sequence: 1/2, 2/3, 3/4, 4/5. It's pretty easy to find a formula for what's going on. The numerator is an arithmetic sequence going up by ones each time. So if I assume that I start my counter off at 0, then the numerator could be written as 1 plus 1n. On the other hand, the denominator, which is going up by ones as well, is another arithmetic sequence. It starts at 2 and goes up by 1n. So I get the formula 1 plus n over 2 plus n, where I'm making the assumption that I'm starting my sequence counter off with 1. That might cause a little bit of consternation because I wrote the sequence up here starting with a 1 and the sequence down here starting with a 0. That index is an awful lot like a dummy variable. It just helps as a shorthand to help us write down what the terms are. If it really drives you nuts, you could try to figure out how to rewrite the same sequence starting with 1 and going up to infinity. Well, in that case, the top will be n and the bottom will be n plus 1. You'll find out that in the work we're going to do in just a bit, it's not going to change anything. But it is always possible to start the sequence off with any number you'd really like. We're just going to use 0 as often as possible because it makes some of the formulas easier. So, now that I've got the sequence of partial sums, I can ask the question, what does this series sum to? Well, it's going to be whatever the partial sums are approximating. And so that means I want to take the limit as n goes to infinity of 1 plus n over 2 plus n. Now we're talking sequential limits, so the first thing I can do is swap out all of those n's for x's and ask whether or not I'm looking at an underlying function. Now this function has only one discontinuity at x equals -2. It has no trig in it whatsoever, and that means it only has a finite number of critical points, and so it is in fact an underlying function. So we should now be able to go and work out its limit using any of the tools of Calc 1 that we've got. We could, for example, apply the leading term test. The limit as x tends to infinity of the original rational function is now the limit of just x over x. The x's cancel, leaving me with just a 1. And so the limit of 1 is 1. Alternatively, if we had the original function, we could test evaluate it at infinity to come up with an infinity over infinity, which means we could hit it with L'Hopital's rule. If we hit it with L'Hopital's rule, the derivative of the top would be 1, the derivative of the bottom would be 1, and once again, we would find that the limiting value is 1. So, the series sums to 1. And we've worked out another series. Let's evaluate the summation n going from 0 to infinity of n over 2n plus 1. So if we work out the sequence, it's going to be 0 over 1, the next term is 1 over 3, the next term is 2 over 5, the next term is 3 over 7, the next term is 4 over 9, and on down the line. And then because it's a series, we're going to be adding up the terms of this sequence, and then asking ourselves whether or not these hone in on a real value. And so we need to focus our attention on the first partial sums. So the first sum is 0. The sum of the first two is 1/3. The sum of the first three terms is going to be 1/3 plus 2/5. On a common denominator of 15, that's going to be 5 plus 6, which is 11. If we add up the first four terms, we're going to have the sum of the first three terms, which is 11/15. Then we're going to add to that 3/7. Now that's starting to get less fun. We're going to get a common denominator of 105, and then 77 plus 45, 202 105ths. If we add up the first four non-zero terms, I guess. We're going to have the sum of the first three, which is 202 105ths. We're going to add to that 4/9. And let's see, putting it on a common denominator of 945, then the numerator is going to be 9 times 212 plus 105, and that's 2,328. And so, by adding up the terms of the original sequence, we've come up with a new sequence. So here's our list of partial sums: 0, 1/3, 11/15, 212, 105s, 105ths, and 23/28 over 945. In order to work out the series n over 2n plus 1, and see if this converges, see if this hones in on a specific number, we've got to see whether or not this sequence Sn converges. Are the terms in this sequence numerically approximating something? But that means we're going to need to come up with a formula for each one of these terms. And that's where this problem traditionally gets harder, is that while it might be really easy to find patterns in the terms of a sequence, once you start adding them up, it becomes a lot harder, in general, to find the terms of their partial sums. Now, maybe you're clever enough and you can do this. Maybe you can see what's going on in here. But I'm actually going to make the claim that this series right here has to diverge. And here's how I'm going to kind of argue it. Let me take a look at just the original sequence, the n over 2n plus 1. And let me take the limit of the original sequence. Now, if I take the limit of the original sequence, I can swap out all of the n's with x's. That would be x over 2x plus 1. It's pretty clear that this is an underlying function. It has one discontinuity and no trig in it. So if I say use the leading coefficient test from Calc 1, I know that this limit is going to be 1/2. So the terms in the original sequence are becoming better and better approximations of 1/2. So what does this mean? Imagine we got out to 100, so we're adding 100 over 201. Plus 101 over 203, plus 102 over 205. Imagine we get really far adding up terms. Well, we know that each one of these terms is pretty much 1/2, almost 1/2. And this one is 1/2, and this one is 1/2, and this one is 1/2, and this one is 1/2. So after we get past, adding up the first several terms, sooner or later, all of the terms in the sequence are decimal approximations of 1/2. And if you added 1/2 over and over and over again, 1/2 plus 1/2 is 1, plus 1/2 is 3/2, plus 1/2 is 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5. The only thing that we can conclude is that if we were to attempt to add up the terms in this sequence, eventually we're going to be adding up a bunch of 1/2s, more or less. And if you add up 1/2 an infinite number of times, it's just going to get bigger and bigger and bigger. And so the only conclusion I can draw is that this series diverges. It doesn't hone in on a specific approximation. Rather, the successive sums just get larger and larger and larger and eventually get bigger than anything you'd want. So now that we've seen some examples, we can start making some sort of technical definitions of what a series is and the notions that we're looking at. So a series, the summation n going from 0 to infinity an, is the formal infinite sum of the terms of a sequence. Now we've seen that by successively adding up these terms, they either hone in on a number or they don't. And so let's formally define those two concepts. We say the series converges if the sequence of its partial sums converge, just like in the examples we've done before. Otherwise, we say the series diverges. Now we've seen in our examples that coming up with a formula for these partial sums is not a trivial task. Even if you know the formula for the terms a0, a1, a2, a3, a4, you still have to add them up, which usually takes a lot of algebra work, and then find a pattern in them. So it's worth noting that our last example illustrated something more general. It suggested that if the limit of the sequence of terms didn't converge to 0, then the series formed by adding those terms must diverge. And the basic idea was because, well, imagine the limit of the sequence converged to something else. Say some teeny tiny number like 100th. Well, then that just means that each one of the terms is a really good approximation of 1/100th once they start getting big enough. So you're going to see lots and lots of terms who look like 0.01, maybe 0.00011, or 0.009999, or maybe you'll see just a couple of 0.1s, but they're all going to be really close approximations of 1/1000th. But that means when you look at the series is what you get by taking the terms and adding them up successively and looking at what you get. Well, eventually in that list, you're going to be adding up terms who have really big subscripts. And that means when you start looking at the partial sums, once you get to this bit back here, you are going to be effectively looking at adding 1/100th each time. And even though 1/100th is pretty small, if you keep adding it up over and over and over again, a number who's about 1/100th, the first 2 of them will get you 200ths, the first 3 of them will get you 300ths, the first 4 of them will get you 400ths, the first 5 of them get you 500ths, but you've got an infinite number of them. After 100 terms, you've got about 1. After 200 terms, you've got now about a sum of 2. After 1,000 terms, you've got a sum of 10. After 1,000,000 terms, you've got bigger and bigger sums. And so if we keep adding up this same small number over and over again, the only thing that we conclude is that this sum here will eventually blow up. That's the basic idea of this result. This result is sometimes called the term test for a series, because you look at the sequence of its terms and you can make a conclusion about what you'd get by adding them up. The idea of a test for a series is going to be a big one for us. But let's take a look at some other examples. Let's find the summation n going from 1 to infinity of 1 over 10 to the n. I should put that proviso now, if it exists. So, we know that this series right here, the summation of 1 over 10 to the n, starting at 1, is going to be, well, let's see, we're going to have 1/10, 1 over 10 squared, 1 over 10 cubed, 1 over 10 to the 4th. There's the terms. We're going to be adding them up. And then we're going to be seeing whether or not these decimally approximate some specific number. Now, let's do the partial sums and see if we can get some headway with that. The first partial sum will be 1/10, 0.1. The sum of the first two terms is 1/10 plus 100th, which is 0.11. The sum of the first 3 terms is the sum of the first 2, which is 0.11, plus 1,000th, which is 0.01, and that's going to get me 0.111. If we add up the first 4 terms, we're going to have the sum of the first 3, which is 0.111, and then we're going to be adding 0.0001, 1/10,000th, which gets me 0.1111. And so actually, we've got 0.1, 0.11, 0.111, 0.1111, 0.11111. So the sequence of partial sums is the decimal point 1 followed by an ever-increasing list of 1s. So now, if we wanted to work out what the sum of 10 to the n is, we simply have to take the limit of this sequence of 0.1, 0.11, 0.111, 0.1111, and identify what that number is. Do you know what it is? Well, I'm going to make one quick change in this. This first number is actually 1/3 times 0.3. The second number is 1/3 times 0.33. The next number is 1/3 times 0.333. The next number is 1/3 times 0.33333. Now you might remember in the last section that we actually stumbled across the sequence already. 0.3, 0.33, 0.333, 0.333. We found that the formula for it was 10 to the n plus 1 minus 1 over 3 times 10 to the n plus 1, where I'm assuming I start the counter off at 0. I actually have this extra 1/3 out in front, and so the limit of partial sums can be written as the limit of the sequence n to the 10 plus 1 minus 1 over 3 times 10 to the n plus 1, starting from n going from 0 to infinity. And so all I have to do is take the limit as n goes to infinity of this sequence, 10 to the n plus 1 minus 1 over 9 times 10 to the n plus 1. In fact, if we run through the exact calculation we did last time, we can show that this limit right here is 1/9. The point of this particular example is to show you again that just because it's easy to find a formula for the terms, it doesn't necessarily mean it's easy to find a formula for the partial sums. However, there is a certain case where a formula for the partial sums is known. People have found it and use it all of the time, and that's the following. Evaluate the sum n goes from 0 to infinity of a to the n if possible, where here a is a constant. Now, if I try to go and work out what the partial sums are, right, this series is going to be the series n goes from 0 to infinity a to the n. So we're adding a to the 0 plus a to the first power plus a to the second power plus a to the third power on down the line. Now, if I try to add up the first one, 1, the second two terms, 1 plus a, the third two terms, 1 plus a squared, and the fourth set of terms here, 1 plus a squared plus a cubed, how can I find a pattern in these numbers if I don't know what to stick in for a? Well, this particular sum of numbers has been studied for quite a long time, and given enough time and enough play, you actually might come up with a formula for what it is. Let me show you what this formula would be. Suppose you take 1 plus a squared plus a cubed, and you add up to the nth term. So you're looking at the nth partial sum. I'm going to multiply the top and bottom of this expression by the same thing. I'm going to multiply the top and bottom by 1 minus a. So I haven't changed anything. Now, if I expand that out, I've got a 1 to distribute through all of these pieces. So if I distribute the 1 through everything, I'm going to have, well, 1 times 1 is 1, 1 times a is a, 1 times a is a squared, 1 times a is a cubed, on down the line. Next, if I distribute the negative a, I guess, through everything, let's see, we're going to have 1 times negative a is negative a times negative a is negative a squared, a squared times negative a is negative a cubed, negative a to the fourth, and on the very, very last one, we're going to have negative a to the n plus 1. All of this is still over the 1 minus a. So let's take a look at what we have up top. You might notice that there's an a here and a negative a here, so those terms cancel. There's also an a squared here and a negative a squared here, and those terms cancel. So pretty much the only two terms who don't cancel are the extreme n's, the 1 times 1 and the a times negative a to the n. So if I clean that up, we found out that the nth partial sum of this is 1 minus a to the n plus 1 over 1 minus a. So we've got a partial sum for the series. That means if I want to work out the limit as n goes to infinity of an, that's taking the limit as n goes to infinity of my partial sum, 1 minus a to the n plus 1 over 1 minus a. We could switch all of the n's with x's. 1 minus a to the x plus 1 over 1 minus a. If we take a quick look at this, the only x's appear up here. This is an exponential function, and so this is a critical function, has no discontinuities, no bends. So we can go and take the limit of it. If we take the limit, we're going to have 1 minus a to the infinity over 1 minus a. Remember, this is a constant right here. This is the only thing who we have to sort of evaluate intuitively. Now, what could it possibly be? Well, if a is a little number, a fraction, smaller than 1, then fractions raised to powers would go to 0. And so, if the value a is less than 1, then the series is going to converge. And it's going to converge to, well, that would go to 0, so we'd have 1 over 1 minus a. So, we've just figured this out. This series is equal to 1 over 1 minus a, provided that a is smaller than 1, but larger than negative 1. In other words, that it's a tiny fraction. What if instead this number was bigger than 1, like a 2 or a 7 or a 1.5? In that case, this expression right here, a to the infinity, in size is infinite. It gets bigger and bigger and bigger, and that would tell me that this thing diverges. So, it turns out I have two cases here. This series will diverge if a is bigger than 1 or a is less than negative 1. I could probably compactly write that as just saying if the absolute value of a is really, really big. You know, one term we didn't talk about is what happens at 1. If a was equal to 1, then this becomes 1 to the infinity. So that's one of my type C indeterminate forms, which means I can't just go and flat out use my intuition. I gotta study this a little bit more. Well, what would it be if you were adding up 1 each time? The summation of 1 to the n. That would be 1 plus 1 plus 1 plus 1 plus 1. I don't even need to look at partial sums for there. If you keep adding 1 over and over and over again, then this series is going to diverge. I guess minus 1 might be another question worth asking. What happens if you plug in minus 1? So you're adding 1 plus minus 1 plus 1 plus minus 1 plus 1 plus minus 1. Well, if I add up the partial sums, I'm going to have 1. Then the second partial sum is 0. The third partial sum is 1. The fourth partial sum is 0. The fifth partial sum is 1. The sixth partial sum is 0. So my partial sums are 0, 1, 0, 1, 0, 1, 0, 1. And that sequence doesn't hone in on a specific value either. So it turns out that this series diverges if the number is greater than or equal to plus and minus 1. Historically, this result is called the geometric series formula. And the minute I've said that name, I'm hoping that you suddenly remember that we're actually looking at something we've talked about before from a different point of view. We know that there's something called the geometric series function, and its Taylor series is 1 plus x squared plus x cubed plus x to the fourth. But we saw last time that this function had a finite radius of convergence. It was discontinuous at x equals 1. And so we knew that the Taylor polynomials couldn't propagate out much farther than 1. And we had an animation who suggested that it looked like it was breaking down at plus and minus 1. Well, this result here is actually telling us that that's true. This result here is telling us that if we have the Taylor series for 1 over 1 minus x at a specific point a, then it actually sums to the value 1 over 1 minus a, provided you don't go any farther than 1 unit away from the center. So this method, this machine of series, can help us to figure out exactly what the radius of convergence ought to be. We've just shown that the radius of convergence of the geometric series is exactly 1. And that's kind of why we brought up the topic of sequences in series. We'd left it off as a cliffhanger for the radius of convergence idea. Now we can come back and bring it full circle. So let's bring this back up here. Suppose we know that a function f of x has the Taylor series centered at c of f nth derivative evaluated at c over n factorial times x minus c to the nth power. If we plug in a specific value a into this, then the Taylor series at a actually becomes a numerical series, a series of numbers, this particular series of numbers right here. If this series converges as a list of numbers, then we could actually write down that the series evaluated at a converges or is equal to f of a. And this is the first time we've been able to lift that weird symbol away and actually assert that a Taylor series is something, not just a list of approximations, not just some connected idea, but quite literally is describing this function. So, in particular, there are a couple of Taylor series whose radii of convergence we actually know now. Our big four. The Taylor series for e to the x, which is 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, can be shown using Taylor's estimate to converge for all values. So we can write e to the x is equal to this for all x's. Or said differently, the Maclaurin series for e to the x has a radius of convergence of 1. The same is true for sine and cosine, so we can write not sine has the Taylor series, but simply sine is equal to 1 over 1 factorial x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth, on down the line. And similarly for cosine. Cosine of x is equal to 1 minus 1 over 2 factorial x squared plus 1 over 3, plus 1 over 4 factorial x to the sixth, on down the line. All of these are true for all x. On the other hand, our geometric series function, 1 over 1 minus x, is only equal to its Taylor series if x stays between 1 and minus 1. So, a different way of saying it is that the Maclaurin series for this function, for 1 over 1 minus x, has a radius of convergence of exactly 1. You get propagation up to 1 unit away, but no farther than that. Let's use this Taylor series idea to compute the following two series: pi squared over 2 minus pi to the 4th over 24 plus pi to the 6th minus 720 minus pi to the 8th over 4,320, and also 0.1212121212. So let's focus on this one first, because this certainly seems more like a power series. So the basic idea of the Taylor series notion is to see if we can recognize this Taylor series, or this series of numbers, as belonging to the Taylor series of some function. Now, if I keep an eye out for it here, these numbers 2, 24, 720, that's 2 factorial, 4 factorial, 6 factorial, and that number right there is actually 8 factorial if we crank our way through it. So what we've got is the series pi squared over 2 factorial minus pi to the 4 over 4 factorial plus pi to the 6 over 6 factorial minus pi to the 8 over 8 factorial. And so we want to see if we can figure out what function this is at what value, and then we can see whether or not the series converges. Well, let's do this in small pieces here. If I wanted to use the Taylor series idea, I have to start with essentially a close relative and see if I can get to it. Now, with these factorials of 2 factorial, 4 factorial, and 6 factorial, that would suggest I'm looking at the even trig function, whose Taylor series is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th. And we know that because cosine has an infinite radius of convergence, this isn't just a power series, it's a convergent series. Now, we're already pretty close to having this series right here. If I go and replace all of the x's by pi's, we're going to have cosine of pi is equal to 1 minus pi squared over 2 factorial plus pi to the 4 over 4 factorial minus pi to the 6 over 6 factorial, which is pretty close to the number we've got up there. Oh, by the way, cosine of pi, -1. So that's almost the series we've got up top. The only thing that's different is that the signs appear to be off by a little bit, and it doesn't have this additional 1 out in front. So let's subtract 1 from both sides. So if I subtract 1 from the left and 1 from the right, minus 1 is -2, and then on the right we have negative pi squared over 2 factorial plus pi to the 4 over 4 factorial minus pi to the 6 over 6 factorial. And if we multiply both sides by 2, 2 is equal to pi squared over 2 factorial minus pi to the 4 over 4 factorial plus pi to the 6 over 6 factorial minus, and we've been able to figure out that this series up top converges to 2. Now what about this series right here? In fact, it doesn't even look much like a series the way it's written, but I'd like to convince you first off that it is. This portion right here is nothing more than 12/10ths. But then there's this portion right here. That portion is 12 1,000ths. Then there's another portion right here, which is 1, 2, 3, 4, 5, which would make it 12 100,000ths. Then there's this 12 right here, which is, let's see, 1, 2, 3, 4, 5, 6, 7. That would make it 12 10,000,000ths. And on down the line. So it turns out that every repeating decimal actually is just a special kind of series. Now, what can we do with this series here? Well, our goal is to see if we can use a Taylor series to describe what's going on here. Now, if I work my way through this, let's see, we've got 12 over 10, 12 over, that would be 10 cubed, 12 over 10 to the 5, 12 over 10 to the 7. And so we seem to have some kind of a series that has a power going up each time, but doesn't have any factorials. So I'm going to start off by trying the series 1 over 1 minus x, whose Taylor series I know to be 1 plus x squared plus x cubed, on down the line. Now, I know that this is the Taylor series, and as long as the absolute value of x is less than 1, as long as we stayed pretty close to the center, then this will be an equality. Now, can you see what you might substitute into this function, into all of these x's, in order to get it to look closer to that? Well, since there's that 10 in the denominator going up by powers, this 1/10, we might try something like this. I could try substituting 1/10 in. Now, if I tried substituting 1/10, that's allowed because it's less than 1. We would get 1 plus a 10th plus a 10th squared plus a 10th cubed. And so the powers of 10 in the bottom would be going up by 1s, but here the powers of 10s were going up by 2s each time. Well, maybe we should try plugging in 1 100th instead. So we would have 1 over 100, 1 over 100 squared, 1 over 100 cubed. That would simplify to 1 plus 100, or 10 squared, plus 1 over 100 squared, that's 10 to the 4th, plus 1 over 10 to the 6th. And this series here looks an awful lot like this series here, except that it's starting with the wrong term. It started with a 12/10ths, so there's a 12 across all of the numerators in the original series, which isn't in the bottom series. And there's also an extra power of 10 in all of the terms in the bottom. So let's just go and take our original series and just multiply it by 12/10ths. So if we take 12/10ths times 1 over 1 minus 1 100, let me scroll myself down just a little bit, get a little bit more room here. On the right-hand side, we would have 12 over 10 plus 12 over 10 cubed plus 12 over 10 to the 5th, all the way down the line. And on the left-hand side, we're going to have 12 times, or 12 in the numerator, and then 10 times, let's see, 1 minus 1 100th is 99 100ths. So 10 cancels, leaves a 10 there. And so we get the value 12 divided by 99 over 10, which is the same thing as 12 times 10 over 99. If I divide both sides by 3, I get 4 33rds, which comes out to being 4 times 10 over 33. I'll write it over here for convenience. That's 40 33rds. And actually, if I pull up a calculator, and I take 40 divided by 33, I get 0.12121212, as I expected. And so we've just found out that the decimal 0.121212 is exactly 40 33rds. And we've worked out another sum using the Taylor series. So let's close the section up by taking a look at a couple of series and seeing if we can evaluate them. So our first series, well, let's write it out and see what we get here. So our first example, the summation n going from 1 to infinity of 2 times 3 to the n over 5 to the n plus 1, if I write out its terms, that looks like, let's see, 2 times 3 over 5 squared plus 2 times 3 squared over 5 cubed plus 2 times 3 cubed over 5 to the 4th plus 2 times 3 to the 4th over 5 to the 5th. And so I've got this particular list right here. So I could attempt to write some of the partial sums down, but these numbers right here, the 6 25ths, the 18 125ths, the 54 625ths, oops, these aren't commas, these are pluses. Now we could simplify these terms and attempt to work out their partial sums. There's the first several partial sums. Now we could attempt to take the limit as n goes to infinity of this list of numbers, but that's going to involve finding a formula for them first. And while I can figure out the bottom is just powers of 5, the numerator's a little bit tricky, 6 to 48 to 144 to 432. Maybe you can find a pattern in those numbers, and if you can, you could take the limit of it. But I'm, generically speaking, not that clever. I am, however, pretty adept at working with Taylor series because it's what we've been doing for a week plus. So let me change gears for just a second. Let me look at this through Taylor series eyes. If I sort of regroup some of my terms here, if I pulled out, say, a 2/3 5 squared from all of these pieces, because I see it's common, I would have 1 plus 3 over 5 plus 3 squared over 5 squared plus 3 cubed over 5 cubed plus. And that looks exactly like the fraction 6 25ths plus 1 plus times 1 plus blank squared plus blank cubed plus blank to the 4th, where the blank has been filled in with 3/5. But 1 plus blank squared plus blank cubed, but that's the Taylor series of the function 1 over 1 minus blank, evaluated at 3/5 by the heredity principle. So this idea of using heredity, or in this case reverse heredity, going from the DNA back to the function, is paid off here. But now we know exactly that this function right here has a radius of convergence of 1. Since 3/5 is in that radius of convergence, I don't have to put a tilde here. I can put a flat-out equal sign. It's equal to this value. And so I get that it's equal to 6 25ths times 1 over 1 minus 3/5. So that would be 3/5. So this first series sums to 3/5. So cool. We've got the first series taken care of. What about this series? So again, if I write out its terms, just so I have some idea of what I'm playing with here. Let's see. The first term when n is equal to 0 is going to be 2 over 1. And then we're going to have 5 over 6. And then we're going to have 8 over 11. And then we're going to have 11 over 16. And then 14 over 21. And then we're going to be adding up these terms because it's a series and not a sequence. So, the first thing that we can attempt to do on this is we can attempt to work out what the partial sums are. This seems like this is more work than I want to, just to find the sums. And then I'm going to have to find formulas for them. So I'm going to try a different approach. Could I try that Taylor series approach? Well, if I write out these numbers, I notice that the numerator is an arithmetic progression. I notice that the denominator is an arithmetic progression. But that doesn't actually jive with any of my functions, right? E to the x has factorials in it, and I don't see a single factorial in this list. Sine of x has odd factorials in it. I don't see an odd factorial in this list. 1 over 1 minus x doesn't have factorials. And so maybe I could manipulate this series to look like 1 over 1 minus x. But I'm not immediately sure how to do that. It might be a relative of 1 over 1 minus x, but it certainly doesn't look like 1 over 1 minus x. There's not something being raised to a power. And we know from the last section that the finiteness of a radius of convergence is inherited, but not the actual radius itself. So even if I could work out what this number is, or what this function is, I may not be able to detect its radius of convergence. So it looks like my Taylor series idea is out. Do we have anything else left? Well, we did have that thing called the term test a couple of slides ago. The term test said you could take the limit of the actual sequence itself, not the partial sums, but the terms you're actually adding up. And as long as those terms don't tend to 0, then you would be golden. Well, let's try that out. This is a nice sequence. And if I replace all of the n's with x's to make this 2 plus 3x over 5x plus 1, I see that this is definitely an underlying function. It has one discontinuity, no trig function, so it only has a finite number of critical points. Even better, it's a rational function, so I could use the term test from Calc 1 and exchange this for the limit as x tends to infinity of 3x over 5x. The x's cancel, and that means I have the limit of 3/5. But since 3/5 is not 0, that means that the series up here is effectively adding up 3/5 plus 3/5 plus 3/5 plus 3/5 plus 3/5 over and over and over again. And so we know that it has to diverge. So the sequence diverges. What about this last example, the summation n going from 1 to infinity of 1 over n? So if we write out what that series is, that's going to be 1 plus a half plus a third plus a fourth plus a fifth plus a sixth. In fact, this sequence is another one that's been studied by people for a long time. It has the name of the harmonic sequence, or the harmonic series, what we get by adding them up. So does the harmonic series converge? Well, on the one hand, I could attempt to add up the pieces and find the partial sums. Sometimes that works and sometimes it doesn't. So the first one is 1. 1 plus a half is 3 halves. And on down the line. Now, hunting for patterns is, again, tricky. It's clear that on the bottom I'm getting factorials in this list. 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. But the numbers 1, 3, 11, 52, 51, I'm not quite sure what I'm supposed to do with those numbers. Is there a pattern to be found? Once again, I'm not saying there isn't a pattern. I'm just saying I'm not clever enough to find it. Maybe you are. So I'm going to put this method on hold for a bit. What about the Taylor series idea? Could we visualize or represent this series as the Taylor series of a known function evaluated at a specific point? Well, actually, we can. You might even remember these coefficients from earlier in class. But we had the Taylor series for ln of x a while ago. The Taylor series for ln of x was 1 times 1 x minus 1 minus 1 half times x minus 1 squared plus 1/3 times x minus 1 cubed minus 1/4 times x minus 1 to the 4th. And on down the line. This was one of the ones we found on one of our first days of Taylor series. Now, notice these numbers 1, 1/2, 1/3, 1/4? That seems pretty good. That's pretty close to what we've got. Imagine on the right-hand side. Let's just focus on the right-hand side for a bit. we take this series and we evaluate it when x is equal to 0. That's going to get me 1 times minus 1, minus 1/2 times minus 1 squared, plus 1/3 times minus 1 cubed, plus 1/4 times minus 1 to the 4th, which simplifies to negative 1, negative 1/2, minus 1/3, minus 1/4, minus 1/5. This is just negative 1 times 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. So what we've done is we've shown that the harmonic series is the successive approximations of the Taylor polynomial for this function evaluated at x equals 0. But what is this function evaluated at 0? Well, you remember what the logarithm looks like. The logarithm at 0 is undefined. In fact, as you get closer and closer to 0, it becomes worse and worse and worse. It blows up. So what does this mean? Well, it tells me this. If the harmonic series converges, it being the Taylor polynomials of one of our known functions, it must converge to the function ln of x, well, negative ln of x, technically, evaluated at x equals 0. But since this value does not exist, it tells me that the summation does not exist either. This series diverges. It's the Taylor series for a function at its discontinuity. And we saw in the power series sections that Taylor polynomials never converge at discontinuities. Now, I grant that that's kind of a sneaky argument right here. Maybe you can make the partial sums argument work. And in the next section, I'm going to show you another technique that will allow us to really conclude for certain that the summation 1 over n doesn't converge. The only thing I want to point out about this example right now is that if we tried to do the term test, if we took the limit of the terms themselves, the sequence 1 over n, the things I'm adding, I do the underlying function test, and yes, 1 over x is an underlying function. I take the limit as x goes to infinity. I would come up with 0. So the sequence of terms converges to 0. Doesn't that say that the summation converges? Isn't that what that test said? The test says if the sequence of terms doesn't converge to 0, then the series diverges. It doesn't go the other way around. Just because the sequence tends to 0, it doesn't mean that the series diverges. And this is historically one of the earliest known examples of that. Now again, I know that this little Taylor argument is a little bit more tricky than the other ones that we've done here, so let me give you one last example. Just consider this series right here. It's the sequence 1, 1/2, 1/2, 1/3, 1/3, 1/3, 1/4, 1/4, 1/4, 1/4. And then it'll be 5 1/5 and 6 1/6 and 7 1/7. Clearly, the sequence an converges to 0 because the terms are becoming smaller and smaller and smaller. You go out far enough in this sequence, far enough to the right, and you're going to get teeny, teeny, tiny numbers. On the flip side, the summation of an, well, if I look at the partial sums, the sum of the first term is 1, but the sum of the first 3 terms is 2. The sum of the first 6 terms is 3. The sum of the first 10 terms is 4. And so I'm adding up bigger and bigger numbers. Eventually, the next 5 terms will get me another 1. So I'm essentially adding 1 in a very, very long fashion. And so that tells me that this series doesn't equal anything, but it diverges. So the moral of examples like these, what can we conclude? The partial sums method is intuitively nice, but hard to use. It makes sense to add up the terms and see what they're approximating, but finding a formula for those partial sums, which is what we need to test convergence, is damn near impossible. The Taylor series idea is great if you can recognize the series and you know the radius of convergence beforehand. We were able to identify one of those series as the geometric series, and now that we know the geometric series had a radius of convergence of exactly 1, we were golden. That second example was trickier because I had to recognize the logarithm sequence, and we don't know the radius of convergence of the logarithm sequence, but we know it can't extend to the value 0 because that was a discontinuity. But if it was a general function, we don't know radii of convergence just yet. In fact, that's why we made this detour. The term test is easy to use, but it's not very conclusive. It's easy for me to take the limit of the terms of a sequence, and if they're anything other than 0, the series diverges. But if they're equal to 0, I can't use this thing. However, bullets 2 and 3 here have a common theme, that the sequence AN, the actual terms involved, can sometimes tell us about the series AN and its convergence without actually computing partial sums. This idea is something called a convergence test for a series, a method that allows us to detect the convergence of a series without working out the partial sums, and it's going to be what we focus the next 2 sections on.